Let's look at the characteristics of an ideal diode. An ideal diode means a perfect diode which has all the properties in their perfect sense without any flaws. Usually a diode operates either in the forward or the reverse bias condition. The characteristics which are expected to be exhibited by the ideal diode can be analyzed separately for these two modes of operations. So let's look at the characteristics of an ideal diode when it is forward biased. The first one we'll look into as zero resistance. An ideal diode does not offer any resistance to the flow of the current through it when it is in the forward biased mode. This means that the ideal diode will be a perfect conductor when forward biased. From this property of the ideal diode, one can infer that the ideal diode does not have any barrier potential. Let's look into the infinite amount of current. So this property of the ideal diode can be directly implied from its previous property, which states that the ideal diodes offer zero resistance when it is forward biased. The reason can be explained as follows. In the electronic devices, the relationship between current, voltage and resistance is expressed by the Ohm's law, which is stated as I is equal to V by R. Now, if the resistance is equal to 0, then the current will be infinite. This indicates that there is no higher limit for the current which can flow through the forward biased ideal diode. Let's look into the zero threshold voltage. Even this characteristics of the ideal diode under the forward biased state can be referred from its first property of possessing zero resistance. This is because the threshold voltage is the minimum voltage which is required to be provided to the diode to overcome its barrier potential and to start conducting. The characteristics of an ideal diode when it is reverse biased. The first one is the infinite resistance. An ideal diode is expected to fully inhibit flow of current through it under reverse bias condition. In other words, it is expected to mimic the behavior of a perfect insulator when it is reverse biased. The next property is the zero reverse leakage current. This property of the ideal diode can be directly implied from its previous property, which states that the ideal diodes possess infinite resistance, that is when it is operating in the reverse biased mode. The reason can be understood by considering the Ohm's law again, which now takes the form of I is equal to V by infinity, which is equal to 0. Thus, it means that there will be no current flowing through the diode when it is reverse biased, no matter how high the reverse applied voltage be. The next one is the no reverse breakdown voltage. Reverse breakdown voltage is the voltage at which the reverse biased diodes fails and starts to conduct heavy current. Now, from the last two properties of the ideal diode, one can conclude that it will offer infinite resistance which completely inhibits the current flow through it. This statement holds good irrespective of the magnitude of the reverse voltage applied to it. When the condition is so, the phenomenon of reverse breakdown can never occur, due to which there will be no question of its corresponding voltage, that is the reverse breakdown voltage. Due to all these properties, an ideal diode is seen to behave as a perfect semiconductor switch, which will be open when it is reverse biased and closed when it is forward biased. Let's look at the VI characteristics of an ideal diode. Now, let us face the reality. Practically, there is no such thing called as ideal diode. What does this mean? If there is no such thing, then why do we need to know or learn about it? Isn't it just a waste of time? No, not at all, really. The reason is the concept of idealizing makes things better. The rule holds good for anything, not only for technical. When we come to the matter of the ideal diode, the truth manifests as the ease with which a designer or a debugger can model, debug, analyze a particular circuit or a design as a whole. Now let's see what are the different types of diodes. The different types of diodes include ZENER diode, PN junction diode, tunnel diode, varactor diode, Schottky diode, photodiode, pin diode, laser diode, avalanche diode and LED, which is nothing but the light emitting diode. Let's briefly discuss about the ZENER diode. A ZENER diode is a specially designed highly doped PN junction diode which is normally operated in the reverse bias condition. The ZENER diode circuit, when we look about it, the ZENER diode is nothing but a diode which is connected in reverse bias position in the circuit. The characteristics of a ZENER diode. So let's look at these things, the characteristics of a ZENER diode. The VI characteristics of a ZENER diode, that is, when the diode is connected in forward bias, this diode acts as a normal diode, but when it is connected in the reverse bias, the voltage is greater than the ZENER breakdown, a sharp breakdown takes place. In the VI characteristics, Vz is the ZENER voltage. It is also known as the knee voltage because at this point the current increases very rapidly. However, the ZENER diode or the breakdown diode, as they are sometimes referred to, are basically the same as the standard PN junction diode, but they are specially designed to have low and specified reverse breakdown voltage which takes advantage of any reverse voltage which is applied to it. The ZENER diode behaves just like a normal general purpose diode consisting of a silicon PN junction when biased in a forward direction. That is, anode is positive with respect to its cathode. It behaves just like a normal signal diode passing the rated current. However, unlike a conventional diode that blocks any flow of current through itself when it is reverse biased, that is, the cathode becomes more positive than the anode as soon as the reverse voltage reaches a predetermined value, the ZENER diode begins to conduct in the reverse direction. This is because when the reverse voltage applied across the ZENER diode exceeds the rated voltage of the device, a process called avalanche breakdown occurs in the semiconductor depletion layer and a current starts to flow through the diode to limit this increase in the voltage. The current now flowing through the ZENER diode increases dramatically to the maximum circuit value, which is usually limited by a series resistor, and once this is achieved, this reverse saturation current remains fairly constant over a wide range of reverse voltages. The voltage point at which the voltage across the ZENER diode becomes stable is called the ZENER voltage, which is nothing but Vz, and for these ZENER diodes this voltage can range from less than 1 volt to a few 100 volts. Let's look at the applications of a diode. First we will see how diode behaves as a rectifier. The most common and important application of a diode is the rectification of AC power to DC power. Using the diodes we can construct different types of rectifier circuits. The basic types of these rectifier circuits are half wave rectifier, full wave rectifier, that is full wave center tapped, and full wave bridge rectifier. A single or a combination of 4 diodes is used in most of the power conversion applications. The diode operation in a half wave rectifier. During the positive half cycle of the input supply, anode is made positive with respect to the cathode, so the diode gets forward bias. This results in the flow of current to the load. Since the load is resistive, the voltage across the load resistor will be same as the supply voltage. That means the input sinusoidal voltage will appear at the load, and the load current flow is proportional to the applied voltage. During the negative half cycle of the input sinusoidal wave, anode is made negative with respect to cathode, so the diode gets reverse biased. Hence, no current flows through the load. The circuit becomes an open circuit. No voltage appears across the load. Both the voltage and the current at the load side are of the same polarity, which means the output voltage is pulsating DC. Very often this rectification circuit has a capacitor that is connected across the load to produce a steady and a continuous DC currents without any ripples. So the next application is diodes in clipping circuits. Clipping circuits are used in FM transmitters where noise peaks are limited to a particular value so that excessive peaks are removed from them. The clipper circuit is used to put off the voltage beyond the preset value without disturbing the remaining part of the input waveform. Based on the diode configuration in the circuit, these clippers are divided into 2 types, the series clippers and the shunt clippers, and again these are classified into different types like positive clipper, negative clipper. So depending on the series and shunt, positive and negative, totally we get 4 different types of clippers. The first one is positive series clipper, negative series clipper, positive shunt clipper, negative shunt clipper. So let's look at the positive series clipper. During the positive half cycle of the input, the diode is reverse biased. So the voltage at the output is 0. Hence, the positive half cycle is clipped off at the output. During the negative half cycle of the input, the diode is forward biased and the negative half cycle appears across the output. Let's look at the positive shunt clipper. The diode is forward biased during the positive half cycle, so the output voltage is 0 as diode acts as a closed switch. And during the negative half cycle, the diode is reverse biased and acts as an open switch, so the full input voltage appears across the output. With the above two diode clippers, positive half cycle of the input is clipped at the output. So next one is diodes in the clamping circuits. A clamping circuit is used to shift or alter either the positive or the negative peak of an input signal to a desired level. This circuit is also called as the level shifter or the DC restorer. These clamping circuits can be positive or negative depending on the diode configurations. In the positive clamping circuit, negative peaks are raised upwards, so the negative peaks fall on the 0 level. In case of the negative clamping circuit, positive peaks are clamped so that it pushes downwards such that the positive peaks falls on the 0 level. Let's look at the diagram for understanding the diode applications in clamping circuit. During the positive half cycle of the input, diode is reverse biased. So the output voltage is equal to the sum of the input voltage and the capacitor voltage. During the positive half cycle of the input, the diode is reverse biased. So the output voltage is equal to the sum of the input voltage and the capacitor voltage. During the negative half cycle of the input, the diode is forward biased and behaves as a closed switch, so the capacitor charges to the peak value of the input signal. So next one is diodes in logic gates. Diodes can also perform digital logical operations. Low and high impedance states of the logic switch are analogous to the forward and the reverse biased conditions of the diode respectively. Thus, the diode can perform logic operations such as AND, OR, etc. Although diode logic is an earlier method with some limitations, these are used in some applications. The figure shows the OR gate logic implemented using a pair of diodes and a resistor. In this circuit, the input voltage is applied. Logic 1 means high voltage and logic 0 means it is 0 voltage. When both inputs are at logic 0, both the diodes are in reverse bias condition and hence the output voltage at the output Y is 0. When any one of the inputs is at logic 1, the diode becomes forward bias and as a result the output is high.